flexural behavior or bending behavior of reinforced concrete beam under the applied loads for, of course, we are discussing reinforced concrete beams. So you can see a beam over here. I can this is a beam which is basically a simply supported beam. We have a pin support at one end and a roller support at the other end. We have an applied load P at a distance A from the left support, and then equal distance, same distance is applied at a distance A from the right support. So it is a symmetric beam. We have same reactions. At left support you have support reaction of P, and then at right support you have again support reaction of P. Width of the beam is B and its depth is H. So if we cut this beam at a location which is at a distance X from the left applied load, so we are actually talking about this section. We have cut it at this point and we have taken this section over here in the bottom. So we have this applied load P at a distance A from the left support. This is the support reaction. We have some shear and moment at that particular point, but in this case our shear is 0. You can calculate the moment at that particular point. Its solution is over here. It comes out to be P into A. You can take moment at this point, so this P is creating a clockwise moment at this point, which is P into A plus X, and then this P is creating an anti-clockwise moment, which is P into X. So if you simplify it, it comes out to be P into A. So coming to the phenomena which is occurring in this case, you have this cross section of the beam. Its width is B, total depth is H, and the effective depth, which is from the top to the reinforcement centroid of the reinforcement, it is D, which is called effective depth. Coming to the strain profile, you have some compression strains applied in concrete and some tensile strains applied in concrete in tension as well. You have some tensile strains in steel as well. This is the neutral axis where there are no stresses and strains applied. Here your strain profile goes from compression to tension. And the distance from the top fiber to the neutral axis is C. You have this theta, which is actually the curvature of this beam. As the load increases, curvature increases. So compression strain increases, this theta increases. So if we plot a graph between the moment at some particular instant and the curvature at that particular instant, so once you start loading the beam, there is increase in the applied moment, there is increase in the curvature. So it starts to increase linearly till the point cracks are initiated in the bottom fibers of the concrete, because it has very low tensile strength capacity. So you have cracks initiated in that section. So there is increase in curvature but no increase in load for a small instant, and then loads are transferred to the steel. So all the tensile stresses are taken by the steel. It again starts to increase linearly. Concrete in top fiber is taking compression, and all these tensile stresses are taken by steel till a point where uh, steel starts to yield. So this is the yielding moment, my, and at this point there is a greater increase in the strain and lower increase in the moment, and it then follows the profile and reaches this maximum point, which is termed as Mn, nominal moment capacity of that particular beam. So we can basically divide this whole profile into four stages. Stage one, where the concrete has not yet cracked. So this is stage one. Then a particular instant when concrete has cracked, and then when all the low tensile stresses are taken by the steel, this is stage three. And when maximum moment capacity has been reached, so that is basically our aim to calculate the maximum capacity, flagell capacity of the reinforced concrete beam, which is the most important stage, which is the stage four. So in stage one, we have uncracked section and materials are linear elastic. Stage two, concrete in tension cracks. Materials are still in linear elastic. They are still behaving in linear elastic way. In stage three, concrete in tension has already cracked. In stage two, material are still linear elastic. And in stage four, that is the ultimate stage, materials are behaving in non-linear, non-elastic way, as you can see over here. And concrete in compression crushes and beam fails. So discussing these stages in detail, stage one, where there is an uncracked section and materials are linear elastic. This is again the same cross section. Strain in concrete and compression strain in concrete, compression strains in steel, and you have some strains in steel as well. And these are compression strains in, sorry, a tensile strain in steel. So you have some compression strain in concrete and tensile strain in concrete, and then tensile strain in steel. Okay. So coming to the stress profile, if you want to calculate the stresses, and I'm talking about the compressive stresses in concrete, so you can use Hooke's law by multiplying modulus of elasticity of concrete by the strain occurring at that particular instant. Before discussing it, we can first discuss the strains occurring in concrete and steel. Your tensile strain in concrete is less than cracking strain in concrete. So your concrete section in tension is still intact. Cracks have not initiated, so it is an uncracked section. Then tensile strain in steel are still less than its yielding strain. So steel is behaving in linear elastic manner. Then compression strains in concrete are less than their proportionality limit in that concrete. Concrete has no specific value for modulus of elasticity, so it changes with the type of concrete and its strength. So, but the concrete which has been used, strain in compression are less than the proportionality limit strain of that concrete, where the stress and strain increase in a linear manner. So concrete in compression is in linear elastic. They are acting in linear elastic manners. So in this region, in linear elastic behavior, you can use Hooke's law by and convert your strains to stresses by multiplying strains by the modulus of elasticity of that material. So coming back to the same point, and the compression stresses in this concrete, you can multiply this strain by its modulus of elasticity. These are the stresses occurring at this point at a particular instant, then tensile stresses in concrete can be calculated by multiplying the tensile strain into the modulus of elasticity of concrete, and then the stresses in steel can again be calculated by multiplying the modulus of elasticity of steel into the strain occurring at that particular instant. You have some moment taken by this section. Your total compressive forces the total stress compression stresses in that concrete section compression multiplied by the total area, and your tensile force is basically a summation of your tensile forces in tension concrete plus tensile forces in steel. Coming to the analysis procedure, uh, you have to first locate the point where your neutral axis lies. So you have to actually calculate C. For calculation of C, you can use transformed area method or moment force equilibrium method. We will discuss it when we will be solving our example problem. In transformed area, basically we will convert the steel into the equivalent area of the concrete, and then we'll solve them. And then in force equilibrium, we will take the equilibrium, basically equilibrium concept of the forces applied in that section, and we'll calculate value of C and locate our neutral axis. And if we ignore the steel, we can still get closely accurate value. But if you want to consider steel used in that particular section, you will have the exact value. And once your C is located, so it means you have the distance uh, of the neutral axis from the top fiber. So if you have located this, now you know what is the location of this point from the neutral axis, what is the location of this extreme point from this neutral axis, and you will know that what where your steel lies. So what is the distance of steel from your neutral axis. So you can use flexural formula. You now can easily calculate this y, and calculating your uh, moment of inertia. You can use this flexural formula to calculate the moment taken by this section at that particular instant. Okay, so then coming to stage two, which is the point where concrete cracks. It is similar to stage one. Only difference is that now concrete has cracked and stresses are not taken by the concrete because concrete section is already a cracked section. So this stress portion taken by the concrete